Hello everyone. In this video, we will cover the distribution functions of Z, where Z is the present value random variable for life insurances. The distribution function big F of Z equals to the probability that the random variable Z is less than or equals to a value, small z. For whole life insurance of 1 on an individual at age X, Z equals to e to the power minus delta times Tx. A graph linking Z and Tx is given by this. The higher the value of Tx, the lower the value of Z. Z is a decreasing function in Tx. Consider a mortality's law. Constant force of interest, mu equals 0.03, and the force of interest delta is 0.08. We have the following CDF. The vertical axis is the CDF value, and the horizontal axis is the value of Z. Relating the two graphs, the maximum value of Z is 1. This occurs when Tx equals 0. And then as Tx approach to infinity, Z approach to 0. An illustration with another mortality's law, Mechams' law, with the following 3 parameters on an individual at age 40, force of interest 0.05, and we get the following CDF of Z. Again, at Tx equals 0, Z is 1. And then as Tx approach infinity, Z approach to 0. With the Morpheus law, and here we have the maximum limiting age, omega equals 100, on an individual at age 55, force of interest 0.06. And we get the following CDF. The maximum value of Z is 1 when Tx equals 0. And then the minimum value of Z occurs at Tx equals omega minus x because we have a limiting age. At this point, the minimum value of Z is e to the power minus delta times omega minus x. Omega is 100 and x is 55. In this illustration, we get the minimum value of Z 0.0672. All right, let's move on to the N-year term insurance. And this is the PDF of Z. Tx less than or equals N, Z equals e to the power minus delta times Tx. When Tx is greater than N, Z is 0. This is the graph linking Z and Tx. Suppose N is 20. Consider the 20-year term insurance. For constant force of mortality, the maximum value of Z is still 1 when Tx equals 0. And then when Tx is greater than N, the individual survives beyond the N-year period. Z is 0. Therefore, there's a probability mass at Z equals 0. This corresponds to the probability that Tx is greater than N, which is NPX. And in this example, the probability that Z is 0 is 0.5488. And then if the individual dies within the N-year period, the minimum value of Z occurs at Tx equals N. The corresponding value of Z is e to the power minus delta N. And in this illustration, the minimum value of z if tx is less than or equals n is 0.2019. And then an illustration according to the Meckham's law. And we have the graph corresponding to the CDF of z. The maximum z is 1. And then when z is 0, the probability is NPX. And we get 20p40. This is a 20-year term insurance. We get 0.3448. And then at tx equals 20, we get z equals 0.3679. And we have a similar pattern for the De Morphius law. And you can verify the numbers. Let's compare the graph of the N-year term insurance with the whole life insurance. When Tx is less than or equals n, that is the right portion of the graph, the CDF value are the same. And then for the N-year term insurance, when Tx is greater than n, z is 0. So there's a probability mass at z equals 0. And then the CDF curve is constant until reaching to the time point here, corresponds to Tx equals n. All right, let's move on to N-year endowment insurance. Reconsider the graph of an N-year term insurance. For the N-year endowment insurance, we have this PDF. When Tx is less than or equals n, the value of z is the same as for the N-year term insurance. And when Tx is greater than n, the value of z is a constant, e to the power minus delta times n. This is the graph relating z and Tx for an N-year endowment insurance. Consider the 20-year endowment insurance. The graph for the endowment insurance is very similar to the N-year term insurance for the right portion of the graph. And then the minimum value of z is no longer 0. The minimum value of z for endowment insurance occur at Tx equals n, which is this point. And the probability that z is equals to e to the power minus delta n is NPX. For Meckham's law, similar logic. And for De Morphius law, we have the CDF curve for the 20-year endowment insurance. How about the deferred insurance? This is the CDF for the whole life insurance. And for the N-year deferred insurance, the PDF of z. Within the deferral period, that is Tx less than n, there's no payment, so z is 0. After the deferral period, tx greater than or equals n, z equals e to the power minus delta times tx. The same value for the whole life insurance. A typical graph relating z and tx is given by this. Consider a 5-year deferred insurance. The CDF for a 5-year deferred insurance for the constant force is given by this purple curve. Maximum at 1 and then stay constant. The minimum value of z is 0. There's a probability mass at z equals 0 when tx is less than n. Therefore, the probability that z is 0 is nqx. And in this illustration, 5qx is 0.1393. And then there is a maximum value of z where z is no longer 1. This occurs at tx greater than or equals n, and the maximum is tx equals n. In this case, n is 5. So the maximum value of z occurs at tx equals 5. That is the value of z equals to e to the power minus delta, which is 0.08 times 5, which is 0.6703. All right, so what is the relationship between the CDF for deferred insurance and the whole life insurance? For deferred insurance, the CDF FZ is divided into 2 parts. The first part, within the deferral period, the probability that tx is less than n is nqx. And then the second part corresponds to the right portion of the graph here. This corresponds to the probability that z is between 0 and z. And therefore, the CDF for deferred insurance equals to nqx plus the probability of this. And the second term is the same as the CDF value for the whole life insurance. That is, the CDF for the deferred insurance is simply you move up the CDF of the whole life insurance by a value of nqx, with the condition that the maximum value of the CDF is 1. And then stay constant thereafter. All right, the illustration for the Beckham's law and the Morpheus law, similar logic. And then for the De Morpheus law here, all right, so these are the 3 illustrations for deferred insurance. All right, let's summarize what we have covered in this video. Okay, we covered the distribution functions. Okay, we assume 3 mortality laws: constant force of interest, Beckham's law, and De Morpheus law. And then for whole life insurance, this is a typical pattern for Z. And then for the n-year term insurance, there's a probability mass at Z equals 0. And the probability that Z is 0 is NPX. And then when Tx is less than or equals n, the minimum value of z is e to the power minus delta n. For n-year endowment, similar shape as compared with the n-year term insurance for the right portion. And then the minimum value of z occurs at Tx equals n with probability npx. For deferred insurance, there's a probability mass at z equals 0, and the probability is nqx. And there's a maximum value of z occurs at Tx equals n. And these are the graphs we have covered in this video. That's it for today's video. Thank you for watching and see you in the next video.